into a habit. So in physical science or in chemistry, we need to measure things, and that's kind of what we're talking about here. But you can't just measure it willy-nilly, because like a meter here needs to be the same thing as a meter like in China or a meter in Indonesia. So we need to take our meter sticks and go back to some sort of reference standard. So mass is just a measurement of how much matter a chunk, mass is a measurement of how much matter an object has. We said all matter is made up of, starts letter A, atoms, yeah. So to me, when you're measuring the mass, basically you're getting a fix on kind of how much atoms you have there. Length is the distance between 2 points. I mentioned a meter. We need to make sure we're all kind of on the same page there. Volume actually goes back to length, but standard-wise. But volume is how much space a chunk of matter occupies. And we might touch on thermal energy a little bit. Now, thermal energy or heat is not the same thing as temperature. But if you take a thermometer, if my finger's a thermometer, and I put my thermometer into something that is hot, okay, I know that if I subject that hot thing to something cool, then basically thermal energy is going to go outward from that hot object. So we know the direction that heat flows based upon temperature. Oops, let me know if I go too fast. Wow, filling in the blanks there.
Can you go back one slide?
I sure can. This one?
Yes.
Cool. And then this slide. So back to my thermometer thing. If I know the mass of the object and the temperature of the object and kind of the thermal nature of the object, then I can get down to how much thermal energy it has. Oh, sorry. Are we all good with that slide? Okay. So this is actually this little chunk of metal that's stored under lock and key, under a double, I have a picture coming up, under double dumbbell evacuated sort of thing. It was in the news like a few years ago because it was like actually losing mass. So that's not good. But they're in, and we've got a copy of it in Washington, D.C., but there in Paris is the world's standard with regard to mass. And if you've been out, done much with scales and stuff like that, they will say that your scales have been calibrated with weights that are NIST traceable back to some hairy big deal standard. They're like pedigreed, okay? So length actually, so here's another standard, regardless of whether you're here and in China or in Indonesia, light will always travel at the same speed. I know, and we talk about this in astronomy, that I know when I turn a light switch, it seems like the light's just there, but actually it takes a certain amount of time for light to get from point A to point B. And based upon that velocity, then we can calibrate our length, okay, which that kind of blows my mind. And then volume, if we have a length that's calibrated, we can go back to calibrating our volume. So when it says 1 cubic meter, and I don't have a yardstick in here, or meter stick, I'll have to fix that. Okay. But if this was maybe 1 meter, and then we go up 1 meter, oh, it's not square, is it? But then we go deep 1 meter, that's a cubic meter. So 1 meter by 1 meter by 1 meter. So of course you guys would tell me, how do I get the volume of a cube?
Length times width times
Like the other one, length times width times height, yeah.
Yeah, there we go.
Yeah, all 3 dimensions. So in this case, And you'll be doing some of that kind of simple stuff tomorrow with measurements. In this case, I have 1 meter times 1 meter times 1 meter. And in working problems, we make sure that we include our units, and then we take our numbers and multiply them times each other. 1 times itself 3 times is, of course, 1. And what's meters times itself 3 times?
To the third.
To the third, yep. So that's all that is. Okay. So, time actually goes to how long a certain spectral line of the element cesium lasts. So, it's crazy. Just isotope number 133. Temperature, we said, actually tells you heat will always transfer from something hot to something cold. And the temperature standard actually goes back to water. And amount, this actually came up the other day. Remember when Becky was like, so what's a mole? Okay, so that is actually kind of a standard amount in physical science. So a mole, okay, if you were to have exactly 12 grams of one form of carbon, 12 grams of carbon, and you went ahead, and it has to be isotope number 12, carbon. If you were to count the carbon atoms, you would have 1 mole of carbon atoms. And 1 mole is equal to 6.022 times 10 to the 23rd carbon atoms right there. So that's a standard. Cool. And this was the highly secured.
What was the formula you just did
What's that?
for the mole?
What was the formula?
You erased it. 6.022 times 10 to the 23rd. What was the last thing you wrote?
Atoms. But it could be anything. In the case of kind of the description I did was atoms. Yep. Yep, yep. And so here is our handy dandy little piece of metal. Yeah.
Standard.
Standard, yep. That's a faux. So, of course, not so surprising, here in physical science, we're going to be going with metric. So instead of English. I know when I was like in 5th grade, my teacher said that you need to learn metric because when you go to gas up your car, you're going to be gassing it up in terms of liters, not gallons. Here, all these years later, you know, when you gas up your car, it's in English units, in gallons, not liters. So these are different types of glassware. Glassware are great in measuring volume. And we're going to talk about kind of which glassware would give you the most accurate volume. But just in general, and I think I might have mentioned this when we checked in, you know, if I compare, remember those white marks are gradations? I compare the gradations here, gradation, okay, versus maybe the gradations over here, okay. I could have 100 milliliters both places, but you guys probably, which one, A or B? How many people think it's A is the best? How many people think B is the best?
B.
Yeah, me too. Why is B better?
Can you little red thing to your
What's that?
line?
The little-
red thing, doesn't it go up and down?
No, that's just a base. That's a plastic
Oh,
base.
at the top of it.
More fine markings. You
More
can do
fine markings.
55, 60, 65, whereas you can only do about 60, 70, 80 on the other one.
Yep, exactly. This is going to give you more accurate because of the fine markings. Yep, this plastic thing, that thing just chugs off, and I don't know why they made graduated cylinders like that. I think maybe they go in their dishwasher better. So this right here is a burette. Burette. And that actually has nice little, even finer gradations. This one These actually are similar. This is a type of flask. This is a volumetric flask, affectionately called vol flask. And the volumetric flasks just have one mark on them. And the one mark is the to contain. So like that would be, looks like a 1,000 milliliter volumetric flask, one mark. And this is a pipette. Remember, no, don't like suck up. Yeah, this is where I said don't use it like a straw. But pipettes, this one just has one calibration mark too up here. It's pretty darn exact. So I think these videos are work. Watch this. So when we're talking about measured quantities, we always have to have units. Of course, little m is meters. Little g is grams. It is case sensitive. Capital L is liters. Bless you. S for seconds. We talked about kind of a cubic meter. So case makes a difference. One that I run into a lot of times is the letter L, capital L for liters, and sometimes people want to make a lowercase. We don't do a period, like a period, like grams is simply G, not GM period. So grams is G, okay. And we don't use the letter S. So it's not GMS for grams, it's just G for grams. Okay. All right. Okay. Metric prefixes. Of course, prefixes give us like powers of 10 relative to what we call the base unit. Now, do you think you have to memorize these? No. But there are 4 you need to know your way around. And I think I highlight them here. The 4 you need to know your way around is kilo, the lowercase k, kilo, means 1,000 times the base unit. So you need to know kilo. You need to know centi, which is what? Centi is
Centimeter?
centimeter, that's right. 1/100th, like cents, if you have cents, it's how many cents in a dollar, 100. So 1/100th. And you know milli is 1/1000th. And then micro is 1/1,000,000th.
And nano is like 9 or something?
Nano is 10 to the negative 9th.
Negative 9.
Yep. Yep. So know those. Speaking of, nano is 10 to the negative 9th, and we'll be talking about this. I think we've got time to talk a little bit about scientific notation. These, you guys told me meter times itself 3 times is meter cubed, right? Okay. So if we go up here, for instance, 10 cubed, do you guys buy this? 10 cubed is 10 times itself 3 times. So 10 times 10 times 10. And that's equal to 1,000. Buy that? So 10 cubed is. So down here, and we'll be talking about this, but if you have, starting with centi, or actually deci, you actually have negative, right here, we have negative powers of 10.
So we move to the decimal point to the left?
Yes, yep. One way to think of it is, remember I said you need to know centi? Okay, centi is 1/100th, and it's 10 to the negative second, that's 1/100th. So basically, this negative, I'm not a math teacher, basically this negative means that we're talking about it in the denominator.
Trivia question.
Mm-hmm.
Does anyone know the symbol for the micrometer?
Micrometer. So micro is one that you're supposed to know. So that's the Greek symbol mu. Mu. Yep. So what is the symbol for micrometer?
Mu.
Mu m. Micrometer. Yep. Very good. Otherwise called a micrometer.
Oh, yeah, micrometer, that's right.
Yeah, I don't know. So know those four. So there they are. Here's the four again. We have kilo, means 1,000 times the base unit. So, and centi is 1/100th times the base unit. Milli is 1/1000th times the base unit. And micro, this mu, is 1/1 millionth times the base unit. Okay. So I picked the centi prefix and just grabbed the meter. So 1 centimeter is equal to 1/100th of a meter. Okay? The term centi means 1/100th base unit. Of course, centimeter is abbreviated cm. Meter is abbreviated m. Now, one of the things then, this third line right here, one of the things we'll be doing in this class is multiplying both sides of the equal sign by the same thing. So if I take the left side times 100 and the right side times 100, I haven't changed anything, right? But the beauty of this, obviously, is that my hundreds will cancel here, and I'll be left with 100 centimeters now is equal to 1 meter. So I mentioned this because honestly, I don't like fractions. So instead of saying 1 centimeter is equal to 1/100th of a meter, I'll go down to here and say 100 centimeters is equal to 1 meter. So they mean the same thing. And if you're like me, it's easy to get these mixed up. Like, I don't know how many times I've had students maybe say 1 centimeter is equal to 100 meters. You know, just concentrate. Okay.
How many inches is in a meter?
Well, there's 2.54 centimeters exactly in
It's
1
like
inch.
39 points.
So yeah, that's true. When you grab a meter stick, if we had one here, it's about 39 inches in a meter. So I've got a few arrows. Anytime you see an arrow, that means memorize. So memorize this relationship. Now we just did metric, right? So we did the whole centimeters and meters and kilo, and now this is actually now not just metric, this is metric in English. So one of the things I want you to memorize is with regard to the distance between 2 points. 1 inch is exactly equal to 2.54 centimeters. Okay, so we'll talk about what the exact, and actually it's kind of cool, it's by definition. Somebody was thinking on the ball and made that happen. I think that's kind of neat. So you don't have to memorize these other two, okay? But these do link the English to the metric. So 1 gallon is approximately equal to 3.785 liters. 1 pound is approximately equal to 453.6 grams. So you do not have to memorize these. I have another arrow though. You need to memorize this one. If I were to scale down my box to, instead of 1 meter, if I were to make it 1 centimeter by 1 centimeter by 1 centimeter, then my volume is 1 centimeter cubed, right? Length times height times width. Okay, and that's exactly equal to 1 milliliter. So notice this is both metric, right? 1 milliliter is exactly equal to 1 centimeter cubed. All right, cool. So we've already seen some powers of 10. So like 10 to the negative 9th, that's pico. That's 1/1,000,000,000th, okay? 10 to the 3rd, that's 1,000, that's kilo. And the reason you would want to use the 10 raised to a power is because you want to make it easier to read and easier to write, okay? So scientific notation uses powers of 10, and it's a way of, I say, packing up very large numbers or very small numbers, which we need to do in physical science. We're going to be talking on Friday about rounding, or it says significant figures, I'm going to say rounding. And I'll kind of show you how if you do pack up a number in scientific notation, it's kind of easier to show your rounding. Okay. And everybody's a little bit different with regard to where they're at with scientific notation. So I'm going to kind of assume that you don't know scientific notation very well in the next few slides. So scientific notation always has a decimal part, we call the coefficient, and times a power of 10. That's the exponent. So this is my coefficient part. And times 10 raised to some number up here. This is my exponent part. So the coefficient needs to be greater than 1, but less than 10. Less than 10. That's it. So 10 raised to the first power is 10. 10 raised to the second power is 10 times 10, or 100. 10 raised to the third power, we did kilo, right? 10 raised to the third power is 10 times 10 times 10, or 10 cubed. You get the idea. 10 raised to the fourth power is 10,000. And 10 raised to the fifth power is 100,000. Makes sense? Cool. Well, anytime you have a negative exponent of 10, that means that basically you have 10 in the denominator. So 10 raised to the negative 1 means 1 over 10 raised to the first power. That's the way I think of it. 10 raised to the negative second means 1 over 10 raised to the second, or 1 over 100. 10 raised to the negative third, it's 1 over 10 to the third, or 1 over 1,000. 10 raised to the negative fourth, it's 1 over 10 to the fourth, or 1 over 10,000. And last but not least, 10 raised to the negative fifth is 1 over 10 raised to the fifth, or 100,000. We're okay with that. All right, so let's look at an example. 455,000. So first off, I want to get my coefficient, and my number between 1 and 10 is going to be 4.55. Yep. So if I write 4.55, you can think of it a few ways, and actually the way I learned it, and maybe you guys did, was you move the decimal place over. okay? And if we kind of convince ourselves how that worked, the decimal was what we say implied right here. We go 1, 2, 3, wait, 1, 2, 3, 4, 5. Okay, so I had to move it over 5 places, and honestly, this is 10 to the 5th. So, however you get there, actually, we would write 455,000, pack it up in scientific notation, as a coefficient of 4.55 times 10 to the 5th power. You good with that? Cool. Okay. You guys, for your homework on Friday, let's do Friday, you're going to have some playing around with this. Okay, let's do a small number. Okay. So, again, if I was going to move the decimal place over, that's kind of how I think of it. Probably you do too. I would move it 1, 2, 3. I'm going to move it 3 places. That's how I think of it. So your number between 1 and 10 is 2.1. And 2.1 times 10 to the 1.001 is that same number. So now we go ahead and rewrite it in scientific notation. This is our coefficient, 2.1, and our exponent part, our power of 10, is times 10 to the negative 3rd. That works? Are there any questions about that? No. Okay. All right then. So this is actually kind of in a nutshell what I was doing, getting
Okay.
to scientific notation. Yes.
So when you move the decimal point to the right with a small number like this, it's to the negative. It's a negative
When
exponent.
you move it to the, yes,
Okay.
yep, move it to the right. And the way I think of it is, you know it's got to be negative because it's a small number to
So
start
up
out with.
smaller, down bigger, greater.
I think so. But what I usually do is find the decimal, move it so you get a number, your coefficients where it now needs to be. And like what you were saying, Becky, is if you move it to the left, it must be a big number, so it's a positive exponent of 10.
Right.
And if you move it to the right, yeah, it's a small number, so it's a negative exponent of 10. Yep, I think so. That's it. So these are 2 slides. These almost look similar to each other, don't they? But the first slide was if it's larger than 10, and this is if it's smaller than 10. Okay? See, like, if I go back, this one, if the number's magnitude is 10 or larger, then you move it to the left. And this is if it's less than 1, then you move it to the right. Yep, not bad. They sure save a lot of hand cramp. So if somebody's being anal and there's like, I want you to use scientific notation, I want you to have an exponent part, but, how do I say this? It's already, the number's already between 1 and 10, then know that anything raised to the 0th power is 1. So 10 raised to the 0th power is 1. So for instance, if somebody, like I said, being anal, and they're like, so pack up 3.236, pack that up in scientific notation. You're like, dude, I don't move the decimal place at all. So you would just rewrite that as your coefficient times 10 to the 0th. Okay? All right. So, I think we have some examples for you guys to, 3 examples, see what you think. Go ahead and take a stab at those. some of you are still working on it, but for the first one, what was the coefficient?
2.31.
2.31, yep, times 10 raised to what power? One more. 8, yep. 2.31 times 10 to the 8th. Very good. How about this one? What's the coefficient? 7.87 times 10 raised to the negative. I think. Yep, I'm liking it. 7.87 times 10 to the negative 7. Very good. Now this one is just a little tricky. I didn't talk about it, but this negative, this magnitude actually rides along with the coefficient. So what is the coefficient for this one? Negative 4.4. Very good. Times 10 raised to what power? 4? I'm liking it. You guys got it. Negative 4.4 times 10 raised to the 4th. Perfect. Ding, ding, ding. Okay, so we'll take a quick look at these. Oops. Look at that. So we'll take a quick look at these that are due on Friday. Fabulous Friday. Let's see. Oh, Friday's a picnic too, so. But we should be fine. Okay. So the first two, 32 and 34, are about packing up numbers, and then 36 and 38 are unpacking numbers. Yes, ma'am.
Okay, I have one question. For the one that, the numbers are in the middle, like 3, 2, 3, 6, that last slide, it was 10 to the 0 equals 1. So how do you write that in scientific notation? You leave it the same times?
Right, times 10 raised to the 0th power. Yep, exactly. And you might run into that in some of these, so I don't know. Okay, any questions about these? Okay, very good. And does anybody need these? Everybody have their text? Does anybody not have the textbook yet? You have your book? Yeah. All right then, we'll see you tomorrow for lab.